right, welcome to class, everybody. Happy snowy Monday and happy last week of class. So today we're going to finish off shortest paths and Dykstra's algorithm, and we'll talk about quicksort. And that's actually going to be the last new material that we cover. So I left Wednesday sort of unplanned, but what I'm going to do, and it's not updated here yet, is I'm actually going to do 2 days of review. So we'll have a day where we can we'll review some of the Java concepts that we covered at the beginning of class. We've had kind of a break from really focusing on Java, but I definitely want to review that, especially just going into 232. If you're taking 232 next semester, you're definitely, I've heard that, you use generics a lot, hopefully you're comfortable with that, but really want to be comfortable programming in Java because you're going to go even deeper on these data structures and algorithms. And then, of course, we'll also review what we've done since the last quiz. And since the majority of the quiz will focus on that, although there'll be some little bit of sort of Java questions on like inheritance and things like that. Yeah. So, and I guess I'll just remind you, make sure that you get the survey done to get that 1 point. Let me know if you have any questions getting to the course evaluation. I haven't checked what our percentage is, but on like completion. I can't see individually who's done the MSU course evaluation, but I can see what percentage of the course has completed it. So I'll check on that. I'll let us know our progress, maybe on Discord. Yeah. Okay. So let's review. The end of last class, we were talking about finding shortest paths in a graph, and I think this is just really cool that there's actually a simple greedy algorithm that finds all the shortest paths just by processing one node at a time and using a priority queue. So that's the reason we're learning about this, is because it is a really important application of a priority queue, but it's also a really famous algorithm, so good to know about. So we talked about graphs where we have nodes and we have edges between them. So again, just like a tree, there are actually a lot of ways that we could implement this, and that's going to be a big thing in 232 is implementing graphs. But for now, let's just assume we have some implementation of a graph, whether it's node objects that then hold the other nodes that they connect to, or some other representation. But we can use these graphs for a lot of useful things, like, say we have, in this example, airports, and our edges tell us the distance between airports. And if we want to know what the shortest path between, say, this Providence airport right here and this Honolulu airport, well, we could look at every possible path to find that. It happens to be this red path here. But there is a more efficient way, and it comes down to really this property 1 here, which I think property 1 and property 2, I think these are kind of related. It's saying that, if the shortest path from PVD goes through ORD and LAX, if this is the shortest path from PVD to HNL, that was not a straight line, then it must be the case that, so this is our shortest path that we're talking about here. It must be the case that the shortest path between PVD and LAX is a subpath of that path. Like it can't be shorter to go over here to get to LAX, but somehow when I add Honolulu at the end, it's now shorter to go this way. And so this is why we're going to be able to use priority queue and just examine one node at a time in order to get all of these shortest paths. And so what our goal is in Dijkstra's algorithm, our goal is we start with one node. So we have our whole graph, and we start with one node, and we're going to be able to write down the total shortest path distance. So that would be, for HNL, it would be 255 plus 849 plus, we got, 255. Doing this in a weird order, but the sum of all the edges that we took to get between them, that would be the shortest path distance between PVD and HNL. We're going to be able to write down those shortest path distances for all the nodes, actually. Turns out the most efficient way to get, even if I just want to know Honolulu, between Honolulu and PVD, it's actually just as efficient to write down the distances between PVD and all other nodes in the whole network. And so that's what Dijkstra's algorithm is going to get us. Yeah, so we can also call, I was calling that the shortest path distance, but we can also call that just the distance of a vertex. And so we often use S to be the vertex that we're getting all the shortest paths for. So in this case, S would be PVD. And then all the other vertices, we will just have them, we'll use the variable V to represent them as we're processing them. And our strategy is going to be to grow a cloud of vertices that starts with S. So we're going to start at PVD, and we're going to expand out. And once we've expanded to all the nodes, then we're going to know all of these shortest path distances. So I think that the best way to understand this is just to see an example. And then we can really see where our priority queue is going to come in. So what we're going to do, so let's say A is our, we want to find what is the shortest path distance from A to every other node. So I can already tell you for sure that like the shortest path distance from A to C, I guess, can anybody tell me what's going to be the shortest path distance between A and C? Yeah, just take the 2 edge, so it's going to be 2. We don't have to test every path to know that. We can just look at it. Our smart human brains know that. Let's see if there's another one. How about F? What's going to be the shortest path distance between A and F?
4 to 5.
So 4 to 5 gives us 9, right? So we know we can get there with 9. So 9, but is there a better way?
2, 1, 5.
Yeah, 2, 1 to 5 is going to be 3 plus 5 is 8. And yeah, that looks like that's going to be as good as we can do. To me, you know, we definitely don't do any better if we say, you know, a really bad path would be to go all the way around here, something like that. Okay, so we know that this one, F should be 8, C should be 2, but what is an algorithm that's going to get us all of those shortest path distances? So what we do is, at the beginning, we know that we're really focused on A, and so what we do is we create a priority queue. And we're going to put all of the nodes into the priority queue, and we're going to just examine the one that has the highest priority, which is going to be the lowest number. So we're going to start off, we don't know anything at all. All we know is that it's a distance 0 to get to A, so I'm going to put A in with priority 0, meaning highest priority, and our priority is going to represent our current best path to a node. And so at the start, we don't know how far any node is because we're just a computer. We don't get to see anything. In order to, our human brains, we could see, oh, B is 8 away, but in our algorithm, we don't know that yet. We just know that B, currently, our best guess for B is it's infinity away. And our current best guess for every node is infinity. So I'm just going to put them down here. Okay, and so at every step of our algorithm, what we do is pretty simple. We just run our remove min. So that's the method priority queue. It just has insert you can put into it, and you can remove the min. And so if we remove min, then we remove, in this case, A. And every time we remove, we are going to update the distances that we can get to from that node. So we're looking at A, and we say, well, we can get to B, C, and D. So we need to update those distances. So to B, now it's not infinity away. It's actually 8 away. Because I see that from A, I can follow that edge, and it's only 8 away. C, I can see that it's 2 away, and D, I can see that it's 4 away. And so, and I also am going to, I said I'm removing this, so I should remove that. And so now, after my first iteration, this is what my priority queue would look like. And so I'm going to copy it over and go on to the next slide. And so here we can see that, in the words of these slides, we now have this, we've examined A. We have this cloud saying, okay, A has been examined. And so what I do next is I say, well, I look at my priority queue. Only thing I can do with it is remove the min. So I'm going to do that. Oops. So the min is now C, right? Because it has a priority of 2. So I'm going to remove C. And that means that I visit C, and so I can update my distances. So from C, I can get to D. And since what I'm doing is I'm updating the distances from A to that node. And so now that I have C at my disposal, what should my distance to D be? So it's 1 from C, but what these priorities are representing is actually the distance from A. So it's 3, exactly. And, we can look at this and we can say, oh, I know it's 3 because I see this path. But we don't need to know what the path actually was. All we need to know was that the shortest distance to C from A was 2. And I can get from C to D in only 1. So I kind of, all I'm keeping track of is this list of the nodes, right? I haven't, I don't need to remember how I actually got there. Does that make sense? That's kind of the key here. The reason we can use this greedy approach is that it doesn't actually matter how I got to C. If I know that I can get there in 2, then I can update the shortest paths to everything that C connects to just by looking at the edge weights on C. So we'll see so from C to D, we can now get there in 3, right? When we only had A, we could get to D in 4, but now that we've added C, we can get to D in 3. Let's see. We can also, C is connected to B as well, but if I take that edge, I could get to C in 2 from A, and if I take this edge, then what would be the distance from A to B? 9, exactly. But my current best route to B is what? It's 8, exactly. And I have that in my priority queue. I actually don't need to even be able to look at the graph. I know that my current best route to B is 8, and so I shouldn't update that because I have a better route there. Great. I'm seeing some nods, so I'm hoping that means that's making sense. Okay, so let's see, we updated D, we updated B. Oh, and then E also has edges to, C also has edges to E and F. So now I can get to F, and it's 9 plus 2, so I can update F's current best shortest path from A, and I can update E's current best shortest path. It's 2 plus 3 is 5. Okay, so now, we've done a couple steps. So I want to show the pseudocode just so that hopefully we can look at the pseudocode and then we'll actually come back and do a couple more examples. So now let's just make sure that we can interpret this. So we started with weighted graph G, and we had our special vertex S. For us, it's A. And in the end, we're going to be able to output the length of the shortest path from S to every other vertex. So at this point, we don't have the actual shortest path length yet, but we're updating it as we go. We made a priority queue that had all the vertices of G, and now we're just going through this while loop where as long as we still have a vertex that we haven't processed, we get that vertex. This is like new vertex to process. And then we look at all of its neighbors. And this is so we saw how when we only update the current best path if it's better than what we currently have. So when we already had a path of length 8, and if we used C, it would have taken us 9, then we don't update that. Okay, any questions on that? We'll keep going through the example. Okay. So we just processed C. So now we finished processing C, so I'm also going to erase it. And so let's move on to the next node. So when I call remove min, which one are we going to remove? Yeah, the lowest one, which is D. So I don't remember where I wrote this last time, but I'm going to copy this over to the next slide. Okay, so we visited C already, it's in our cloud, and now we're going to visit D. So okay, D is, we're not going to go back to A, so we won't look at that edge, but D does connect us to F. And so if I go so I can get to D in 3, and then if I take this edge to F, then it's only going to be 8 to get to F. And so I update F's current shortest path to be 8. And then I think I've done everything I can with D because it only had 2 edges, or I guess 3 total, but we've already looked at 2 of them. And so we're done with this iteration. And so we would keep going. I'll copy this over. to the next slide. And again, now we would remove E, etc. And so we keep following this process until we have visited all the nodes. And so you may have noticed I wrote down that priority queue, but we also have those shortest path distances written down for each node here. And so, I guess this is our actual final one right here. And so now we have the shortest path distance from A to all other nodes, and we really had a pretty simple process to get there, I would say. So just to try to see how we're doing for understanding, why would it work? I guess, would it work if, so we always removed the minimum value in our priority queue, right? Like, for example, maybe we'll do this one. I think let's go back here because we still have it written down. So we could have expanded to any node that, I guess, as long as it has an edge. Well, we actually could expand to we could expand our cloud anywhere, but we always expand to the thing that comes out when we call remove min. Does anybody have any thoughts? Like, what would happen if instead we were taking any old node and expanding through any node? Would we still, what does it get us that we are taking our current shortest path in a way?
Would it be that we might miss like a shorter path because we're going the long way?
Yeah, I think that's a great way to think about it. I mean, we're using this fact that if you have the shortest path, if you have the current shortest path to a node, as long as I guarantee that at this point I have the shortest path to a node, then adding one to it is going to also be a shortest path. But if I don't pick my current sort of best, then I might break that guarantee on the next iteration, I guess. There was some other, I had some other question in my head, but, oh, yes, okay. So let's say we've done this, we've executed Dijkstra's algorithm, I've got all these numbers in circles, but I mean, I kind of started with this motivation of like Google Maps or something like that, where you say, I want to get from A to E, but what information do I have right now? Or do I actually have, from what I told you, could you actually tell me what the shortest path from A to E is? You can definitely tell me what how long is it? It's 5. It's 5, I know that I can get from A to E in 5, but have we actually recorded any information about what that path is? Yeah, I'm seeing some heads shake, and you're right, we did not record that. Any thoughts on how, if I wanted that information, what might I do as I'm going? Yeah.
So it's kind of represented, it has like a dash blue line, that's the they're leaving information out. But like, are we gonna make a tree of this as we go along, like branching off from the shortest path?
So yeah, I guess the book wanted to highlight the fact that, and I'll erase this all. So the book wanted to highlight that these shortest paths form a tree, which is kind of the same way, similar or possibly equivalent to our observation that shortest paths must be subpaths of other shortest paths. And so here we do have this tree, but as we were going and recording this priority queue, we actually didn't retain what those edges that we took were. But yeah, I guess anyone else have any thoughts on what might we do if we did want those? Yeah.
You just take like a value, and then every time you remove, you add it to the value. Does that make sense? Like if you're like, I'm gonna remove C, then you just add C.
Yeah, okay, so you're saying, like here, we processed A. I guess okay, so here we first removed A, and then our next step was to remove C. So what value are you thinking that we might keep? That's okay. So I think the one that I would think of is that what we could do is we could just record the edge that got us to. We don't have to record the whole path back. So at the end, we don't have to say for E, we don't have to have that E, that the path was A, C, E. But if what we do is we record the last edge, so E came from C, and when we popped off C, or when we called removement on C, if we also had remembered that C came from A, so we just need to remember the node that it came from, then we can always work backwards and we can ask ourselves, so here what we would do is we would have not just these numbers saying what the distance was, so we're saying E was 5 away, but we also say, well, E, its shortest path to A, its last node was C. And so now we need to follow that edge to C. And then C would also have not just that its distance to C was 2, but also, or to A was 2, but also that it, in this case, it's kind of silly. Of course it came from A. But again, we're a computer. We don't get to look at the whole graph. And so we can just remember one single node, the node we came from, and we can always trace that path back. Yeah.
What if B had a distance of 3, so it was the shortest path to B, just A to B was the shortest path? Would it ever get removed? Because you just went A, C, then you never go to A again. So what do you do?
Yeah. So you're saying, yeah, so if this was 3, let's see, where were we? Maybe here. So if this was 3, and so then what would happen is that we would process, instead of processing D after A, so let's see, where did our cloud go? Oh yeah. Well, I guess they would end up tied, and then it wouldn't matter. So at that point, we could either process D or B, but certainly after processing D, then if this had been 3, then B would still have a current best distance of 3. And so we would then have processed B. And then we'd have 2, I guess. In that case, it would just depend which one we chose, whether our shortest path to E was through ABE or through ACE. But since they have the same, either one would be fine. Okay, cool. So that's Dijkstra's algorithm. You'll definitely hear about it, and it is an application of a priority queue. That would be the thing to remember for the quiz. Okay, the last thing we're going to talk about in this whole class, the last new thing is quicksort. So first off, I guess if you're going to invent an algorithm, you might as well call it quick something, so that everyone knows how good it is. But so quicksort, also a recursive algorithm like merge sort, but it has a different approach. At a high level, I would say that the work is done on the way down the recursion tree. So in merge sort, it's really easy when we're going down. We're just like, okay, find the middle, recurse, find the middle, recurse, find the middle, recurse. And then the hard part is hard. I mean, it's not that hard, but the hard part is merging the sequences back together. Quicksort, on the other hand, does the hard part, which of course is just splitting up the lists on the way down. And so I guess since a lot of you have probably started Project 5, please stop me if you have specific questions about quicksort, since you've probably already looked at it. Otherwise, I am going to kind of just proceed introducing it. But please do stop me if there's something that was confusing in the code that you used. So, first off, quicksort was until like the last 10 years or so, maybe something in the 10 or 20 year range, quicksort was actually the fastest, the most used sorting algorithm in practice. Now it's something called timsort, but in practice it's used in a randomized fashion. We're not going to get into too many details on this. So yeah, we'll talk about this at end. But basically the idea is that we're going to pick any element, and we're going to call that the pivot, and we're going to look at all the other elements. So in this picture, the heights are supposed to be the values. So, this might be like 3, and this one's 2, and this one's 4, and this one's 5, and this one's 6, 7, 8, right? So what we do is, once we've chosen that pivot, then we're going to divide our list into the things that are smaller. So we're going to call that the left side. The things that are equal, so if there's only 5, for example, and 5 is our pivot, then there's only one thing in the equal bucket, and the things that are greater. And so in this case, this was a really nice, lucky one, right? Because we had only 3 things that are less, 3 things that are greater. And so this is a nice, just like merge sort, we kind of divided our list in half. And then, so now that we've divided, and this is the work, right? So recursive algorithms can feel like, when are you actually doing the sorting? Well, this is the sorting, is putting the smaller things on the left and the bigger things on the right. And then we just say, well, sort the left, sort the right, and then once you get back down to a base case, then return the things on the left, put them on the left, return the things on the right, put them on the right. I think when we are analyzing quicksort, it says it on the slide already, but if we are creating these lists, so suppose I've chosen my pivot X, how much time does it take to create my L list my E list and my G list? Or how would I create those? I mean, it's in the, if you've worked on project 5, then you've implemented this or at least pasted the code in. But if I needed to go from this to L, E, and G, what would be the algorithm to do that? Yeah, go for it.
After you might have to take your limit, maybe you would do a for loop going through the elements of the list and sorting them according to order less than or greater than.
Yeah, exactly. It's really simple. I already know, I've chosen my pivot. In this case, it's 5. And I'm just going to walk over my whole list. For loop would be the perfect tool for that. And I'm going to say, okay, 8, are you less than 5 or are you greater than 5? Or are you equal to 5? Well, it's greater than 5, so it's going to go into the G bucket. 4, you're less than 5, so you're going to go into the L bucket. 6, you're going to go into the G. 2, the L. Kind of, I guess I won't compare to myself, but if there was a 5, if there was another 5, because there can be, we don't need any guarantees about our elements being unique, so there could be multiple 5s in here. They would go in the E bucket, etc. So what would we say the runtime of that process is? Yeah, big O of n, we just walk over the list one time. Maybe we have to do some, put something into a list. Okay, that's a primitive, we make a comparison, that's a primitive operation. We put something into a list, that's a primitive operation, but that's just going to be a constant factor. And so overall, big O of n, time to do that. So that's why we would say that the partition step of quicksort takes big O of n time, because we just have to partition into those lists. All right, so this is the code that you have on project 5. So we can come back to this if we want, but let's do a quick example. Again, just depicting those recursive calls using a tree like we saw for merge sort. So here, So here we happen to have selected 6 as our pivot. And so what's going to happen? Well, we're going to divide into our left, our equal, and our greater groups. And we're going to quicksort left. So that's why we quicksort onto those smaller numbers. Now pick a random pivot. It's a 2. So now we're going to call quicksort on the left again. So we're going to call quicksort on the 1. It's a single element list, so it's already sorted, so I can return. So when I return, I'm going to put this 1 on the left of my sorted list. So it's going to be a 1, and then at the moment, we need to fill this in. We need to recurse down the right side of this tree. And, okay, the slide skipped some steps. They said, okay, let's see. 2 was our pivot, so now we're going to have to recurse on the greater than side. So the 3 and 4 are greater than 2, so we recurse down here. We happen to choose 3 as the pivot. There's nothing less than 3, so we only come down here. But once we come back up, so this is one call. 2 was our pivot. We put the 1 on the left, and then we just put the thing that came back up on the right. And so this is why we say we do the work on the way down, because the work is just splitting up into the partition. When we come back up, we just put what you just gave me on the correct side. And so I think we're good. I guess, are there any questions on tracing through quicksort? It's another, I would say, sometimes kind of feels magical, just partition your list, but that is how recursion will maybe feel for a while. Okay, so the last two new things I want us to get out of this class. Worst case runtime for quicksort, and some idea of how we get our expected runtime. So, should have edited these slides so that I could ask when is going to be our worst case. But, okay, so this slide is telling us the worst case is when the pivot is either the minimum or the maximum. So let's say that, let's look. Okay, so we've got this list here, right? 7, 2, 9, 4, 3, 7, 6, 1. So why is the worst case going to be picking let's say the maximum element every time? Let's say we're unlucky, really unlucky, and every time I'm going to pick the maximum element. So first I pick 9, and then I end up picking 7, and then I pick 6, and then I pick 4, 3, 2, 1 in that order. So why is that going to be my worst case? Yeah, so I'm really not dividing. I'm just, I'm not dividing. I'm not making my input size, say, around half. And if I'm picking the big numbers every time, so remember we create the set of L elements, the set of E elements, and the set of G elements. So if I pick the biggest number every time, which one of those is big and which one is small? So maybe we look at the pseudocode. Okay, so the big idea is we're going to make this. We divide our original set into the one set that we call L, one set that we call E, and one set that we call G. And the L's are the smaller ones, the E's are the equal ones, and the G's are the greater. So if we're always choosing the biggest one, then the L is going to be really big every time. So the lower numbers are going to be big every time. Okay. So worst case, like we said, if we always choose the minimum or maximum, we're not dividing. And in this picture would actually be, I guess, can anybody tell me what this picture is which are we choosing the minimum or the maximum in this picture? What was that? Yeah, why would you say that? Yeah, so if I choose the minimum, like I chose 1, and let's say that was the smallest one, then 1 would already be a 1-element list, but all the big numbers would be on the right. Bigger numbers. And since in the worst case, we're only taking 1 off every time, then this recursion tree depth would end up being exactly n-1. But in general, big O of n is what we would say the depth of that recursion tree in the worst case is. And we already said that it takes us linear time to do that sorting, figure out partitioning, figuring out who goes in L, who goes in E, who goes in G. And so that means we do that n times, it takes big O of n time, and that's where we get our worst case runtime of big O of n squared. And you might look at this and say, well, aren't these getting small? Like at the end, I'm only partitioning a really small set. But that doesn't really help us asymptotically, because same way that something like insertion sort is big O of n squared time, right? The first time, if you remember insertion sort, we start from the left of our list, and, well, it's not hard to sort that. You know, it's already sorted. We move on to the next thing, and we put it in the right place. Well, even though those early ones don't take very much time, in the end, it ends up being big O of n squared. I would say the same logic would get us to this being big O of n squared. However, what ends up saving us, and the reason that this works really well in practice, is that when we do choose a random pivot, we're usually not going to be choosing, we're usually not going to be in this bad case. And so what we can do is actually use probability theory to analyze the expected runtime. And where this comes is you have a good chance of actually choosing what we would call a good pivot instead of a bad pivot. So we write down some numbers here, but it's not like these numbers aren't magical. We could have chosen slightly different numbers and we could still get the same analysis. The key is that there are lots of ways to pick good pivots and not so many ways to pick bad pivots.
Why don't we just calculate the midpoint for the pivot?
Well, let's see. If you knew it,
Oh, because it's not sorted.
yeah. I think if you knew what the middle was, then you probably could do something better than, yeah. The idea is you wouldn't know what the middle is. And so then, once we have that our expected, in expectation, we are going to divide in half or so every time, then we end up with really similar analysis to merge sort. And so that would be the takeaway for now, that in expectation, the analysis of quicksort ends up being really similar to merge sort. And in practice, it works really well. So you're going to keep seeing it in algorithms classes. And yeah, that is all I wanted to get across today. So come ask questions if you have them, and see you on Wednesday. Yeah.
The lab from last week.
Oh, sure.
So I still
Yeah.
haven't gotten it to work.
Oh, yeah. And that we would want to work for project 5. Yeah, so I actually have a lot of time tomorrow. I don't think... Here, let me... Actually, I should stop the...
I'm a TA for